Dear friends, today we will discuss I/O interfacing with Intel 8085. The technique that we are going to discuss today is I/O mapped I/O technique. Let us now discuss the essentials of I/O interfacing. The 8085 microprocessor has two instructions for data transfer between the processor and I/O devices. I/O here means input and output devices. The two instructions are in followed by 8-bit port address, out followed by an 8-bit port address. Both these instructions are used for IO mapped IO type of peripheral interface scheme. IO mapped IO is often known as peripheral mapped IO also. Now it is a 2-byte instruction and the second byte is for port address. So if the second byte is a 8-byte, then there are possible combinations 256. So a total of 256 types of ports are possible for in and out. Let us try to understand how the instruction works. Let us take an example of out instruction. Now the example here is out comma 80 hex. Here the 80 hex means the port address. Now suppose we are writing the program across the memory location 8000, 8001, 2 and 3. Now in this case, this first instruction means MVI A47. Here it means load 47 immediately into accumulator. Now after the execution of this particular instruction, 47 will be written into accumulator. Now the next instruction is out 80. Now whether we are talking about in instruction or out instruction, both this instruction are attached with accumulator. So when the microprocessor is going to execute this particular instruction, it will see what is there in the accumulator. So out 80 hex means the content of accumulator that was previously 47 will be available at the output port whose physical address is 80 hex. Let us look at the timing diagram of out 80 hex. Now before we try to understand the timing diagram of out 80 hex, we need to first understand that the first 4 T states, that is the first machine cycle, is meant for fetching the operational code. The next cycle, either it will be completely dependent on the previous operational code. If the machine requires for a memory read, then there will be a second machine cycle, or if again the machine requires another machine cycle, then there may be a third machine cycle. It all depends on the operational code that was decoded inside the machine. So let us first consider the opcode fetch. In this we have 4 T states, namely T1, T2, T3 and T4. Now if we consider the out instruction which was previously mentioned, where the out instruction was written across the location 8002 and 8003. So at corresponding to 8002, the operational code of out was written. So first of all, the microprocessor needs to read the operational code, or actually fetch the operational code, decode that, and only then the machine will be able to understand what sort of operation is required. Now in the first T state, it is basically the addressing mode. So here you can see it is working with the memory. So IO M bar is low. Now S1 and S0 are all 1, means it's in the fetch cycle, and the upper address bus is presently having 80. So the upper address of from where the operational code will be fetched is in the upper address bus. The lower order address bus is having 02. That means the total address is 8002. Now in the next T state, that is T2 and T3, the lower order address bus will be released and the operational code will be taken inside the microprocessor. The operational code of out is D3 and hence it has now entered the microprocessor. The machine gets ready in the T4 state, but it is incomplete. So in order to complete the cycle, it has to read the port address. Since it's an out instruction, the microprocessor needs a port address, so it will go for a machine cycle again where it will be a memory read, and the similar process will be on where the operational code the operand or the data or the physical address, that is 80, is available across 8003. So again the first T state will be meant for addressing, and the last two T states, that is the T6 and T7 of this machine cycle, will read the data into the microprocessor. Now the microprocessor is having the physical address inside it. In the third cycle, since it's a out, that means something is going to go out of the microprocessor, so it will be a IO cycle. That is why IO M bar is now high, and it will be a memory write cycle. So in the first T state, we can see that the higher address bus is also having the 80 physical address, and the lower order address bus is also having the same physical address. So we have to remember one thing in case of 8085. For the simplicity of decoding, the manufacturers have created the microprocessor in such a manner that whenever out instruction is executed, the upper address bus also carries the same physical address as well as the lower order address bus. So the system manufacturers and the board system manufacturers can decide whether to use this for decoding purpose or this for the decoding purpose. Now since we have the physical address right now in the microprocessor's program counter, now the lower order address bus is again released, and the 47 that was initially inside the microprocessor is now written into the port having the physical address 80. Similarly, let us try and understand the in instruction. In this example, we can see we have a address in 81 hex. Here the in is the operational code or the instruction that needs to be executed, and 81 is the physical address. Now let us assume that it has been written across the memory location 8000 and 8001, where DB is the operational code of in and 81 is the physical address. Now we have already seen and we know that the accumulator is by default attached with these two instructions. So here anything which is available in the input port, in the input physical port at the physical address 81, suppose it is E0, so after the execution of this particular instruction, E0 which was available in the input port will now be written into the accumulator. Now let's again see the timing diagram. It is exactly similar to the out instruction, but only the similarity is the last machine cycle where it is a memory read, because the information from the outside world, that is in our example it is E0 which is available in the input port, is now going to get inside the microprocessor. So whenever anything is going inside the microprocessor, it is read, and anything going out of microprocessor it's write. So again in the first machine cycle, the operational code is fetched, and then the execution in the T4 state is partial. Here everything is kept ready inside the microprocessor, so that the information that is presently available at the input port will be written into accumulator. In the next machine cycle, the 81, that is the physical port address, is read by the microprocessor in the similar fashion. It is read by the microprocessor as is evident from this. And in the third machine cycle, we can see that the accumulator content will now be filled with the available data, that is E0, which is available at the physical port of the input port. Now let's see the procedure, how the interfacing is carried out in IO mapped IO method. The first thing that we need to do is decode the address bus to generate a unique pulse corresponding to the device address on the bus. This is called device address pulse or IO address pulse. Now we have to combine the IO address pulse with the device select pulse. That is, the next procedure should be combine the device address pulse, that is, this is the device address pulse, with the control signal to generate a device select pulse. That is generated only when both the signals are asserted. Means we have to make sure that the microprocessor reaches the IO devices in a unique manner. That means, first of all, the instruction needs to be a IO mapped IO instruction. It has to be in or out. Then the port address that are given should be decoded, and along with the port address there should be a pulse coming from the IO read or IO write, and combining only those two. Only after that the input or the output port will be accessed. Let us now try and understand using this figure. Now let us assume that the input port address is 81 and the output port address is 80. Now, for instance, suppose the microprocessor is presently giving out an instruction which is out 80. That means presently the microprocessor is trying to communicate with the output. So the upper address bus information and the lower address bus information will be same as seen here. The same thing will be transferred to the output of the octal latch, and the lower 3 bits are directly connected to the decoder, and the one that is from A7 is directly connected to the active high enable of this latch. Then A6, A5, A4 and A3 are decoded using a bubble NAND gate, where all are 0 means the output will be 0, and it is connected to E2 and E3, where E2 and E3 are active low type enable. So A7 to A3, all this signal ensures that this particular decoder is active. Now when it is 000 here, we will get the O0 output high. So we have generated a device select pulse. Take it. It is the device address pulse. Now since it is an output port, we will be using IO write, which is 0 right now because the instruction is out. So this 0 and this 0 will create a low pulse at the output of this, and hence this will get activated. But what about the other port? The other port, you can see, since it is 000 here, this O1 will be high, and When the microprocessor is in the write mode, it cannot be in the read mode. So this is high. So 1 and 1 will create a 1 at the output, and hence the input port is presently disabled. So what we can see is when the microprocessor is generating out 80, it is uniquely identifying the output port, and the content which is presently available in the accumulator, which was 47, will be available at the output of this. Similarly, let us try to understand if the microprocessor is trying to get information from the outside world into it using the in port or the in instructions. Now let's see, the microprocessor is presently generated 81 hex. That means it is presently trying to execute in 81 instruction. So similarly, the upper address bus and the lower address bus will have the same information. Now the latch, because of ALE, the same information will be available outside the latch, and since the lower 3 bits are 001, it will actually enable the output O1, but for that we need to enable the entire decoder. To do that, we have a 1 from A7 and we have a 0 from the bubble NAND gate. So this signal ensures that the decoder is active, and this ensures that the O1 is active. So what we can see is, since this is 001, this will become deactivated and hence it is disabled, the output port. But the input port, this becomes 0. Now it is in the read mode, so it is 0. Output will be 0, enabling the buffer, and the E0 information available at the input of the port is now will be transferred through the data bus into the accumulator. So far we have seen that to generate IO address pulse for input port device selection, all the address lines except A7 are at ground low. Now this is because A7 is directly connected to the active high enable input of the decoder. The logic low through address lines A6, A5, A4, A3 are directly connected to the bubbled NAND gate. This will generate an active low enable signal which will enable the decoder. Now A2, A1 and A0 are directly connected to the input of the 3-line to 8-line decoder. Now the output of the decoder O0 will get selected when A2, A1 and A0 are low. Along with the control signal, we can select either the output port or the input port. Okay, so if we are talking about the output port, then the address lines A2, A1 and A0 are at logic low. Will select the output O0, and along with the control signal IOW, that is IO write, will generate a IO select pulse, finally enabling the octal latch and transferring the data 47 through the data bus from the accumulator to the outside world. Therefore, the port address for the output port will be 80. Similarly, the address lines A2, A1, A0 when at logic 001 will select the output O1, and along with the control signal IOR, that is input output read, will generate an IO select pulse, finally enabling the input buffer of the input and the data E0, which is available at the input port, will be transferred to the data bus and to the accumulator. We all know the accumulator is attached with the input and output instruction. Therefore, the port address of the input port will be 81 hex. To summarize, we have in this lecture discussed the concept related to I/O interfacing. We have discussed I/O mapped I/O technique along with its interfacing diagram, where we have seen the technique of absolute decoding both for input and output and the related timing diagrams. Hope you have enjoyed the video, and if you like the video, kindly subscribe to the channel iNet Tech Talk. Thank you very much for watching the video.